Hello everyone, I'm Wesley Assunção from PUC-Rio and I'm going to present this work done in collaboration with amazing colleagues. In this paper, we present a multi-criteria redesign strategy to modernize legacy features as microservices. The evaluation of the proposed strategy relies on an industrial case study. Well, despite being outdated or obsolete, legacy systems represent a massive and long-term investment in organizations, regardless of their business domain. To keep such knowledge and take advantage of new technology, legacies have been modernized with microservices. However, to modernize legacies with microservices, developers have to figure out which feature and how to redesign the source code. The redesign consists of identifying and analyzing implementation of legacy features, often structurally degraded, in order to redefine a new design structure. Redesigning legacy systems into microservices is quite complex. There is several studies on this topic. Despite their contribution, proposed approaches are mostly manually applied or only some tasks are automated. The existing strategies are not feature-driven, so engineers cannot select only the features they want to modernize. Also, these studies do not discuss about further decomposition of features and sub-features. Regarding the criteria used for the identification of microservices, most approaches rely on the traditional coupling and cohesion. The last limitation is that several studies do not consider the industrial context in which the system has to be migrated. To cope with the limitations, we proposed a multi-criteria design strategy. Here, redesigning encompasses the identification of boundaries in the source code, where the legacy system should be split in microservices. Our strategy is based on both static and dynamic analysis and search-based optimization. We reflect upon the benefits and drawbacks of the proposed strategy through an industrial case study, and such reflections are also based on observation of developers and maintainers of the legacy system. Our strategy is composed of 4 steps and requires three pieces of information as input and produces a microservices-based architecture as output. To represent the legacy in our strategy, we adopted a generic representation based on graph, which allows our strategy being applied in any kind of legacy system. Use method level representation to reach a better modularization, since legacy systems often have very large files where many features are tangled to each other. As shown in this figure, each vertex in the graph represents a method mapped to the feature it realizes. Each edge represents the relationship between methods, describing syntactic and dynamic calls between them. By default, our approach adopted 4 criteria for microservice identification, which relies on finding from our previous work. The criteria are based on 3 different perspectives: traditional criteria to evaluate the actual structure of the legacy, which are coupling and cohesion, a microservices-based criterion that estimates the network overhead when dependent features are migrated to different microservices, and a criterion based on feature modularization to guide the redesign of custom microservices. The details on how to compute each criterion are described in the paper. In a previous study, we have observed that the criteria adopted by our strategy are interdependent and conflicting. Based on that, these steps relies on a many objective search-based approach, adopting the NSJ3 algorithm. As I mentioned, the representation of solution is based on a graph. The fitness functions are the criteria selected in the second step of our strategy, and all objectives were designed for minimization. Regarding the operators, for the selection, we adopted a binary tournament, which individuals are randomly selected from the population, and then the best ones are chosen to undergo mutation. And the mutation operator consists of moving methods from one microservice candidate to another. This is similar to the move method refactoring. The output generated by the optimization is a set of solutions, each one with different trade-off among criteria. In these steps, software engineers need to choose which solutions fit better their needs. For example, they can select a solution that most reduces network overhead or increases feature modularization. In this figure is an example of solution with two microservices, as you can see by different colors. This solution represents an adequate solution considering feature modularization, for example. Our evaluation was guided by 4 research questions. The first research question investigates if microservices proposed by our strategy are aligned with business capabilities. The second one focuses on the relevance of adopted criteria for the microservices identification. RQ3 addresses the impact of search-based technique parameters on the redesign. And finally, the last question focuses on the potential customization and reuse opportunities of the proposed microservices. Our case study relies on a legacy from the oil and gas domain that is developed and maintained at TechGraph Institute. This legacy system is predominantly written in Java and has been maintained for more than 15 years, having a degraded architecture. Currently, the system has limited feature modularization with high tangling and scattering of features. The legacy systems originally was developed to be used in a private network. However, about 3 years ago, the customers asked for new requirements such as making the system available on the internet and using a cloud infrastructure. This motivated the modernization. In this case study, we focus on business capabilities of high value for the clients. These features are authentication, algorithm, and project. To map the features to the code, we implemented an automatic technique based on the execution traces. This technique executes functional test cases to label the vertices with the name of the features they implement. For the relationship information in the edges, static calls between methods were extracted from the system under analysis by a tool called Depth Finder. For the step of identification of microservices boundaries, we configured 3 different experiments with different numbers of microservices, namely 5, 7, and 10 microservices. For the qualitative study, we interviewed 8 developers of the legacy and inquired their opinion about some generated solutions. About the results. In the first analysis of the results, we can see that the solutions have different compromise among the 4 criteria, as you can see in this parallel chart. For example, coupling and cohesion are conflicting measures, as we can observe in the solution by the yellow and black lines. On the other hand, coupling resembles network overheads in half of the cases. This is expected result, since when there is more coupling, more is the communication among microservices and vice versa. An interesting observation is that structural cohesion is not strictly related to feature modularization. For instance, cohesion in classes code does not lead to cohesion in features. Then, approaches that rely only on cohesion might violate the principle of single responsibility. To qualitatively analyze the redesign candidates found by each experiment, we pick up the solutions that represent the best trade-off among the objectives for each experiment. As we expected, the parameters related to the number of microservices directly affect the granularity of microservices. Here we can observe the context of sub-features, which are part of the main feature, however with their own scope. For instance, algorithm analyzer that we can observe in these candidate solutions is a sub-features of algorithm. To answer the first research question, we asked the developers of the legacy to check whether they recognize the microservices that represent business capabilities. We could note that with 7 and 10 microservices, the two experiments, some new features were identified by the developers, which were not previously informed as known by them. This slide presents some comments from the developers. In summary, the activity of evaluating the generated solution allows the participant to reason about the features and their sub-features, and they agreed with the predominant feature modularized in each microservice. Also, we analyzed which criteria the developers have considered during the evaluation of the solutions. Most developers have considered all 4 criteria. Feature modularization, coupling, and cohesion were mentioned by all developers. Network overhead was considered by 3 developers. Other criteria considered by the developers are related to team size, developer knowledge, or quality requirements such as performance and security. In this research question, we addressed the impact of the number of microservices in the generated solutions. We observed the impact in the criterion values. For example, the solution with 5 microservices might be the ideal solution in terms of coupling and cohesion. However, given the coarse-grained microservices, the value of network is extremely high. In terms of feature modularization, despite of the difficulty for modularizing cost-cutting features, our strategy found good alternatives. An answer for this research question 3 is that the obtained redesigned candidates composed by microservices with different granularity levels show that our strategy is flexible and able to generate solutions according to developers' needs and preferences. For the 4th research questions, we observed the 3 types of customizations that can be explored in the redesigned microservices: interface customization, microservice specialization, and disabling a microservice. Also, developers identified opportunities of customizations and envisioned reuse opportunities of 4 microservices from the solutions obtained by our strategy. So, in conclusion, in this paper we introduce a strategy to redesign features as microservices. The strategy uses a many objective search-based technique, optimizing coupling, cohesion, network overheads, and feature modularization. An industrial case study has shown that the proposed strategy achieves promising results and calls for further investigation of its use in other legacy systems. In summary, the main findings of our study is that the legacy features were modularized as microservices aligned with business capabilities. The developers of the legacy systems consider mainly the 4 criteria included in our strategy, and reuse, also customization opportunities arose from the redesign of microservices. In this sense, a future direction is to propose an explicit criterion related to variability to support configurability of microservices. That is all. Thank you for your attention, and I open for any question.